Good morning everyone. So recall that in the last class we were discussing regular singular point, and we know that if x naught is a regular singular point, then the solution would be of the form summation a n x raised to the power n plus r, where we need to find the values of the value of r by finding the initial equation, and its roots gives us the values of the r. So we have discussed two cases in the last class. If r1 r2 let's say be the root of the initial equation, so the first case is they do not differ by an integer. So the difference of r1 r2, if it is not an integer, then there exists two linearly independent Frobenius solution, and each one corresponds to a value of r. If r1 is equal to r2, then there exists only one Frobenius solution. So these two cases we discussed in the last class. There remains two more cases. Both the cases are related to when they are unequal, r1 r2 are unequal, and they differ by an integer. So the first case says that r1 is not equal to r2 and r1 r2 differ by an integer. It means their difference is an integer, and there is a coefficient of y of x which is arbitrary for a value of r. In that case there exists two Frobenius series solution. But what does it mean? So let us say that there are two roots m1 m2, where m1 is the smaller root, and there is one coefficient am which becomes arbitrary for r is equal to m1. Arbitrary means we cannot find its value. A naught is arbitrary, but other than a naught, if for that value of r we cannot find am, then there exists two Frobenius series solution. But this is important. So there exist two Frobenius series solutions where coefficients are a naught and am. It means we get both the solutions for r is equal to m1 only. We don't have to compute the solutions for r is equal to m2. It would be more clear once you see this example. So let's assume that we need to solve or find the Frobenius series solution for xy double dash plus 2y dash plus xy is equal to 0 about x equal to 0. So clearly x is equal to 0 is a regular singular point, and we can write down y. Now if I substitute the value of y, then it would be summation a n plus r n plus r minus 1 x raised to the power n plus r minus 2 but multiplied by x, so that's why, plus 2 a n plus r x raised to the power n plus r minus 1 plus the last one is xy dash, so a n and x raised to the power n plus r plus 1 is equal to 0. Now first let's try to find the initial equation. So equating the coefficient of x raised to the power r minus 1, it is the lowest degree term, so you just need to substitute value of n to be 0 and see what is lowest degree term. So it gives you a naught from the first term r, then r minus 1, from the second term a naught r, and in the third term there is no coefficient. Now a naught is not equal to 0, it means r square minus r plus r, oh sorry, there is a 2 also, so plus 2r is equal to 0, that gives you r square plus r is equal to 0, and that gives you r is equal to 0 and minus 1. So here roots differ by an integer. It means it is case 3 or some other case. Let's see. So now equating the coefficient of x raised to the power n plus r minus 1 is equal to 0. So it will give you a n plus r minus 1 plus a n and 2 n plus r, and the last term is giving you a n minus 2 because it is n plus r plus 1, so a n minus 2 is equal to 0. So if you simplify it, then it will become a n, and it is n plus r whole square minus n plus r plus 2n plus r, so plus n plus r is equal to minus a n minus 2, and that gives you a n is equal to minus a n minus 2 divided by n plus r plus 1 and n plus r. Yes. Now one important observation here is that r is equal to 0 and minus 1. So if I put r is equal to minus 1, so for r is equal to minus 1, my an is minus an by 2, then n, because r is minus 1, and n minus 1. Yes, and similarly for r is equal to 0, I can write down the recurrence relation. Now let's move further. I wrote this recurrence relation because if I put r is equal to 0 also, an is equal to an minus 2, and then n plus 1 and n. So here if you see it, I start from n is equal to 2 and none of the coefficient is getting arbitrary. So now one more important observation is that n starts from 2. It means I cannot compute a1 from this recurrence relation. Also remember what is a recurrence relation. So recurrence relation is, you should write an in terms of its preceding terms. For example, in an minus 1, an minus 2 and so on. So now the coefficient of x raised to power r minus 1 gives me a naught. It means the coefficient of x raised to the power r gives me a1. So coefficient of x raised to the power r. So if you compute it, you will find a1 r plus 1 plus 2 r plus 1 a1 is equal to 0, or implies a1. If you simplify it, this is how it looks like. So now this is a very important observation. If you put r is equal to minus 1 here, then both the sides become 0 0. So for r is equal to minus 1, a1 is arbitrary. This is very important observation. For r is equal to 0, you can see that a1 comes out to be 0. So now for r is equal to minus 1, you get a1 arbitrary. It means you will get both the Frobenius series solution for r is equal to minus 1. So r is equal to minus 1 gives us both Frobenius solution. Yes, now we have already computed how the recurrence relation looks like for r is equal to minus 1. So r is equal to minus 1, an would be minus an by 2 and n minus 1. n minus 1. Yes, now quickly substitute the values. So if you substitute the values and you will try by yourself, then you will see that you are getting the solution in terms of a0 and a1. So you will get y of x as a0 and r is minus 1, so x raised to power minus 1, 1 minus x square by 2 factorial and so on, and then a1 x raised to the power minus 1, x minus x cube by 3 factorial and so on. Now very important observation comes into the picture. This can be written as a0 x raised to the power minus 1 x square by 2 factorial and so on. And this, if I take x raised to power minus 1 inside, x raised to the power 0, 1 minus x square by 3 factorial and so on. So now if you see here, then this series, if I take x raised to power minus 1 inside, then it is not defined for x is equal to 0. This power series solution does not exist. But in second case, when I took x raised to power minus 1 inside, the power series solution still exists, because this is the solution for r is equal to 0. When you put, so it is solution for r is equal to 0. So when you put r is equal to 0, x raised to the power 0 is there, and this is why I told you that we will get both the Frobenius series solution for r is equal to minus 1, because for r is equal to minus 1, one of the root gets arbitrary. So second solution you can compute also, but it already get computed, so it saves our time. Now the last case is, if a coefficient is infinite for r is equal to m, then there does not exist a Frobenius series solution for r is equal to m. This means that there exists only one Frobenius series solution. So this is case 4. Again, it happens when roots are unequal and they differ by an integer. So in previous case, when one of the coefficients is arbitrary, we get 2 Frobenius solution. In this case, we get 1. So let us consider this problem: x square y double dash plus xy dash plus x square minus 1y is equal to 0 about x equal to 0. Yes. So it's a regular singular point, therefore y of x looks like this one. Now substitute the values. So an and n plus r minus 1 x raised to the power n plus r plus an n plus r and x raised to the power n plus r. Again it was multiplied x square first term, the second term is multiplied by x, then x square is there, so an x raised to the power n plus r plus 2, and the last is an x raised to the power n plus r. First let's compute the initial equation. So if you get the coefficient of x raised to the power r, it would be a naught. From the first term I get r minus 1, from the second case I get a naught r, and third one does not have, and the last one a naught. You solve it, then r comes out to be 1 and minus 1. They differ by an integer unequal. It can be either the case 3 or case 4. Now let's get the general term. So if you equate the coefficient of x raised to the power n plus r and simplify it, then you will get an is equal to minus an by 2 n plus r minus 1 n plus r plus 1, n is greater than equal to 2. Yes, it means your recurrence relation look like for r is equal to 1, it is an minus 2 divided by n plus 2, and for r is equal to minus 1, your an is an minus 2 and n minus 2. In both the cases n starts from 2, but if you see for r is equal to minus 1, when you compute a2, it comes out to be a naught by 0. A naught is arbitrary, it means a2 is infinite. It means there exists only one Frobenius solution for r is equal to 1. For r is equal to minus 1, so for any value of r, if one of the coefficient gets infinite, then there does not exist a Frobenius solution for that value of r. It means for the other value there exists a Frobenius solution. Now rest is simple. If you compute a naught, it comes out to be 2.4 for r is equal to 1. a4 is a naught to 4 square 6, and so on. Also, one important observation is you cannot compute a1 here because it starts with a2, and if you cannot compute a1, you cannot compute a3 and so on. So for a1, equating the coefficient of x raised to the power r plus 1 to 0, I will get a1 as r plus 2 is equal to 0. Yes. Now for r is equal to 1, your a1 is 0. Now a1 is 0, it means if you use the recurrence relation, you will get all the other O terms would be equal to 0. It means your y of x is x raised to the power r, which is x raised to the power 1 a naught 1 minus x square, and you compute 3-4 terms, that gives you the required answer. Okay, so in total there are 4 cases, especially the case 3 is critical, or even you can say case 3, case 4. Both are very important. Let's try the last question of this section, which says that solve or find the Frobenius series solution for xy double dash minus y dash plus 4x cube y is equal to 0. Please do try it by yourself and then you can see the answer. So again, x equal to 0 is a regular singular point. I am going into the detail, and if you solve it and get the value of r comes out to be 0 and 2, so differ by an integer. Now if you get the recurrence relation, this is how it looks like. An is equal to minus 4 an minus 4 divided by n plus r minus 2. Now the problem is it starts from 4, A4. It means A2, A1, A2, A3 are missing. So to compute A1, A2, A3, we need to compute them separately. X raised to the power r minus 1 gives us A naught. So I need the coefficient of x raised to the power r, x raised to the power r plus 1 and x raised to the power r plus 2. So equating coefficients of x raised to the power r, x raised to the power r plus 1 and x raised to the power r plus 2 to 0. See what we are getting. So please do try it by yourself. So x raised to the power r gives you a1 r plus 1 minus r plus 1 is equal to 0. Yes, so for r is equal to 0 and 2, a1 is 0, not a problem. X raised to the power r plus 1 gives us a2 r plus 2. Please do verify by yourself. Implies a2 is equal to 0 for r is equal to 2. But for r is equal to 0, this terms becomes 0. Therefore, a2 is arbitrary. But a2 is arbitrary for r is equal to 0. It means r is equal to 0 gives us both the Frobenius solution. But we need a3 also, so let's compute it. So x raised to the power r plus 2 gives us r plus 2 r plus 3 minus a3 r plus 3. Here also it's a3. And that gives you a3 is equal to 0 for r is equal to 0. So now for r is equal to 0, your recurrence relation is an is equal to minus 4 n minus 4 by n minus 2. And now I know that I will get the constant in terms of a0 and a1. So from here I start with a4. So a4 is minus a0 by 2. So minus a0 by 2 factorial. Then the next is a5. So a5 you got in terms of a1, but you just computed that a1 is 0. So a1 is 0, it means the remaining term would also be 0. So and then a3 is also 0. So next is a6, which is minus a0 by 3 factorial. a8 is a0 by 4 factorial. But your a1, a3, a5, a7 all are equal to 0. Yes, but at the same time you can see that your a2 is arbitrary, so you will get the solution in terms of a0 and a2. So your y of x is x raised to the power r is 0, so a0, and a0 is a0, a4, a8, and the a2, a6 is there. So this is a2. So a0 is 1 minus, and next is a4, then a8. I can write it as x raised to the power 8 also, but you will realize that this power series solution is well known. That's why I am writing it like this. So you got the solution in terms of a0 and a1. Also you can see that r is equal to 2. So if you take x square common, then it is multiplied by x square. So this means that the next solution corresponds to r is equal to 2. So this is a0 cos x square plus a2 sin x square. So that's all from today's class. Thank you very much.